Alright, so our first topic here for this video is going to be on formal characters here. So we're looking at characters, I guess it's characters but formal is what I was essentially going to say. I think you can get that yourselves from what we're seeing here. So let lambda and h star be, as always, the lattice of integral linear functions. If v is v lambda, lambda in lambda plus, we want to consider a formal sum of weights, say mu in pi lambda. Each mu occurring with multiplicity of their weight. However, we know that pi plus nu already has a meaning. So I guess I'll just tag this onto this sentence here. So we introduce the group ring, kind of confusing name, of lambda over the integer denoted then z of lambda. And this z lambda is a free integer module with basis elements which we label E as lambda in, of course, a 1-to-1 correspondence with the elements lambda and lambda, with addition denoted E lambda plus E mu. And this z lambda becomes a commutative ring if we set that E of lambda times E of mu to be E of lambda plus mu in our original sense. This gives us our identity of 0. And of course we're going to extend by linearity. So then the file group acts naturally on Z lambda by permutation, by permuting the E lambda as for sigma in our file group, sigma of E, I just don't really need the parentheses there, sigma of E of our root lambda, or I guess it's not a root, it's an integral linear function lambda, is E of sigma of lambda. Now, we define the formal character CH V lambda, or just CH of lambda of V lambda as the element which is the sum over mu in pi lambda of mu lambda m lambda of mu, multiplicity essentially of mu, times the associated element of Z lambda of the group ring, I guess I should be calling it. And we see, of course, that we can extend this summation to all of our capital lambda as if mu's not in pi lambda m, the multiplicity of mu is just going to be 0. So those terms will take care of themselves, I think. For example, if we're in SL2F, I'm sorry, I'm getting kind of distracted here. The formal character of V lambda is given by character of lambda is E of our lambda plus E of our lambda minus alpha all the way through this string up until E of lambda minus m alpha, with, of course, m being the length of the string as angle bracket of lambda on alpha. More generally, if V is an arbitrary finite dimensional, of course, L module, by Weil's theorem and our classification from before, there is an essentially unique decomposition as V being V of lambda 1 plus through V of lambda t, with each lambda I being in lambda plus. So CH3 is the sum of CH lambda I may be called the formal character is the formal character of V. Notice that each, I guess I should write, notice that each symmetry in the Weyl group fixes CHV since our sigma will permute the weight spaces which occur in irreducible summands of V. And knowing this lets us recover the irreducible constituents of V because of a proposition which we're going to state right now. That proposition is that let F be the sum over our lambda in lambda of C lambda E lambda for, of course, C of lambda being in Z, be fixed by all elements of the Weyl group permuting these rates. Then F can be uniquely written as an integer linear combination of the CH lambda and the proof first we have that F is the sum over our lambda in lambda of C lambda times the sum for sigma in the Weyl group E of sigma lambda I think that's right, and I can permute them to make sense. For each lambda in lambda plus such that the size of lambda is non-zero, the set of dominant integral linear functions less than our lambda is finite. Let MF be the totality of such mu, and we're going to let lambda and lambda plus be maximal among the lambda and lambda plus with C of lambda being non-zero, and we're going to set F prime to be F minus C of lambda times the character of lambda here, the formal character of lambda. So clearly F satisfies the hypothesis of our proposition. we know that the dominant mu figuring in CH lambda all satisfy mu less than lambda, so they all lie in M of F. This gives us that M of our F prime, the totality of that, is contained within our M of F. And this is proper because we know that we have our lambda definition not going to be an M of F prime. So by induction, on the cardinality of MF, we can write our F prime in the desired form. So then F does also, sorry about that, there are things happening. To start the induction, note that the cardinality of MF being 1 is trivial. As in this case, a minimal dominant weight lambda, say, is the only dominant weight. In F. So F is the character, this is the weight of lambda times the formal character of lambda. So that the character of lambda is the sum over the sigma in our val group of E sigma lambda. Alright. And our next, with our next topic, we aim to look at, like, what you get from being able to do this here. Oops. In a proposition, going to let V and W be finite dimensional L modules. Then the character of V tensor W is a formal character of V times the formal character of W. Proof. First off, we know that the weights of V tensor W are those of the form lambda from V plus the weight of a mu from W, and occurring with multiplicity is a sum for pi plus pi prime being equal to lambda plus mu of mv of pi mw of pi prime, and as this agrees with the formal multiplication of the characters, we are done. And that's the end of this chapter. So up next we are going to be looking at characters here from a more formal sense, it looks like. Characters. So we want to prove a theorem of Hurst-Chandra on characters associated with the infinite dimensional modules Z of lambda for lambda in H star, as we've seen. We use this to obtain a simple algebraic proof of Weil's classical result in characters of finite dimensional modules. We'll prove a theorem of Chevalier on lifting invariants. And it says here, kind of callously, none of this depends on Freudenthal's formula, which, sure. So, first topic in characters is invariant, polynomial, functions. If V is a finite dimensional vector space, the symmetric algebra on the dual space remember that I called this S because they use some weird symbol for it, is called the algebra of polynomial functions on V. Because keep in mind that the symmetric algebra is like essentially the tensor algebra, except with the tensors being assumed to be commutative. And this is denoted for some reason with a B of V. For a fixed basis, did we cover this already? This seems familiar, but maybe I'm just... like, I know we did a lot of polynomial work in Bourbaki. Maybe they went through this construction. I don't remember exactly what their formalization of this was. For a fixed basis of the dual space, B of V is identified with the algebra of polynomials in n variables, which we label with the elements of the basis of V star. And so we're going to be considering the algebra of polynomial functions on both L and its Cartan algebra H. Now, Since the weight lattice lambda spans H star, the polynomials in lambda span the algebra of polynomial functions on H by polarization, which they leave as an exercise, the pure powers lambda and k, for of course lambda being in lambda and k being a positive integer, already suffice to span the algebra of polynomial functions on H. Now consider the Weyl group, which we know reacts on H star, and hence is going to act on its algebra of polynomial functions. Now we're going to let BH to the Weyl group be the subalgebra of polynomial functions fixed by every element in the Weyl group. This is the algebra of Weyl invariant polynomials. Polynomial, they call polynomial functions. On H. For example, FL is SL2 of F with fundamental dominant weight lambda, then the algebra of Weyl invariant polynomials, I did not write that right, is the algebra with one generated by our lambda squared. If we write sum of f as for the sum of all distinct Weyl conjugates of f in the algebra of polynomial functions on H, then we know that the collection of all conjugates of all Weyl conjugates of lambda to the k is going to span the Weyl invariant polynomials of H. And that is because each lambda in lambda is Weyl conjugate to a dominant integral linear function. Now we're going to let G be the inner automorphisms of L, which we know is generated by the exponentials of the adjoint of the nilpotent elements. Then G acts naturally on the polynomials of L via sigma f of x being f of sigma inverse x, for of course sigma being in G and f being in B of L, and we denote the fixed elements of the polynomials of L by BLG, keeping in mind the G is the inner automorphisms of L. These are the inner automorphism invariant polynomial functions on L. Now, we can construct some inner automorphism invariant polynomial functions by representation theory. As follows. Let phi be an irreducible representation of L onto V. Of highest weight lambda and lambda plus. Let Z be in N as the union for positive roots, L of L alpha, and sigma be the exponential of the adjoint of this Z. Define a new representation, sigma gamma of L to the general linear of V by phi sigma of x be phi of sigma of x, for of course x and L. Which you can check is, first off, check it actually is a morphism, and check that it is irreducible. If V plus in V is a maximal vector, and beta a positive root, then phi sigma of x beta of v plus is phi of 1 plus the adjoint of z plus the adjoint of z squared over 2 factorial, and so on x beta. On v plus is going to be 0, since the element, gonna need a new page. The element of L in parentheses is in N. Moreover, phi sigma of H of V plus is phi of H plus the bracket of Z plus H on V plus, which is phi of H on V plus, which is lambda of H on V plus, as the bracket of Z on H is an N, and phi of N of V plus is 0. What this is saying essentially is that V plus is now a maximal vector of weight lambda for this new representation. So our two representations are equivalent. So they're essentially saying that their L module structures are isomorphic. Now, let psi sigma be a map from phi to v be an L module isomorphism such that psi sigma of phi of x of v is going to be psi sigma of x, phi sigma of x on psi sigma of v for all v in v. Which is a change of basis in v and we see, I should write this on a new sentence, the matrices of phi of x and phi sigma of x, being phi sigma x, are similar. And have the same trace. If k is a positive integer, the function x to the trace of phi of x to the k is sigma invariant. And this we see. So there's a lot of noises happening here. This is a polynomial function. Jeez. as starting with the linear of course, coordinate functions. Of phi of x, the entries of phi x to the k become polynomials in these. And the trace is a linear combination of such. Such polynomials, that is. Note that the invariance of the trace is independent of our original choice of base, or positive roots for that matter. And even by choice of h, so that the function ascending x to the trace of phi of k is x is fixed by the generators of G. Hence by G. Right, now the whole point of this is to compare BL of G with BH of W. So the polynomials of L that are exponential adjoint, that are inner automorphism independent, with the polynomials of H that are Weyl independent. So any polynomial function f on L restricted to H is a polynomial on H, polynomial function on H. This is obvious as if a basis of H is extended to a basis of L, and f is written as a polynomial on the elements of the dual basis. If f happens to be invariant by the inner automorphism invariant, it is fixed by each of our inner automorphisms we constructed before, taf of alpha, for alpha being a root. But keep in mind that our taf of alpha restricted to H was just the reflection of alpha, sigma alpha, which generate the Weyl group. So we see that the restriction of f to H is now a Weyl invariant H polynomial. So we get an algebra homomorphism theta from the, I don't know why I wrote the beta all of a sudden, with the inner automorphism invariant elements polynomials of L to the Weyl invariant polynomials of H. And this gives us with a theorem. This is by Chevali, I believe is how you say his name. which states that this data is surjective. So every vowel invariant polynomial can be found as in H, it can be found as the restriction of an inner automorphism invariant polynomial in L. And the proof, this is the proof by Steinberg here. Now we know we can just show that each element, that each symmetry of K is in the image of our theta. And we show this by induction on the partial ordering of our lambda plus, starting with our lambda minimal, possibly even 0. Sorry about a bit of an interruption. No other mu in lambda plus can occur as a weight of the irreducible representation phi, 1 second, whose highest weight is lambda. And by previous theorems, we see that the sole weights of phi are the Weyl conjugates of lambda, each of multiplicity 1. Now the map from x to the trace of phi of x to the k is a G-invariant polynomial. Polynomial function f whose restriction to H is the sum of lambda k, which is thus equal to theta of f. For the induction, we're going to fix a lambda in lambda plus, k in z plus. Let sigma, let phi, I don't want to call sigma, again denote the irreducible representation of the highest weight lambda f be the function of sending x to the trace of phi of x to the k and the restriction of f to h is symmetry of y k of lambda k plus the sum of c lambda of mu k times the symmetry of mu to the k summing over the mu strictly less than lambda, mu in lambda plus. The terms with mu less than lambda can be lifted to the inner automorphism invariant polynomials of L by induction. So the symmetry group of lambda to the k is liftable. Now, there's one last note we want to make here over a couple of paragraphs. So, we call a polynomial function x to the trace of phi of x to the k as above a trace polynomial. Fx as xx plus xn is the Jordan decomposition of x. And then phi of x into phi of the Jordan decomposition is the Jordan decomposition of phi of x and so then we know that phi of x of s and phi of x of n commute. All terms except phi of xs to the k in the expansion of phi xs plus phi x to the n to the k are nilpotent since they all involve a term. Yeah, hence R of trace 0. Thus, a trace polynomial is completely determined by its values at semi-simple elements of L. And the proof above, the proof of Chevalier's theorem actually shows that theta maps the subalgebra I in BLG generated by the trace polynomials onto B of H to the W. In fact, theta restricted to I is also injective. As theta of f being 0, means the restriction of f to h is 0. Each semi-simple element of L lies in some maximal toral subalgebra hence, by a previous result, is conjugate under G to an element of H. And this is showing this. Oh, so F vanishes on semi-simple elements of L. So F is 0. By some algebraic geometry, which we're not going to do, I guess, immediately, it can be shown directly that theta is injective, so that BLG is generated by our trace polynomials. And we will be in the future writing the inverse of theta, but it says here that this doesn't actually depend essentially on the injectivity of our theta. And yeah, we went over today, but we're gonna call it here. Things are happening in my house. I don't even know what, so I'm gonna go find out what that is going on there. Thanks for watching, I guess, potentially.